Okay guys, so let's continue. So we saw that we can have high order systems, and we did in the previous class, high order systems. So in high order system we can write that y over x equals to, you have s plus z1 means zeros of the system, plus z2 s plus zm divided by s plus p1 pole of the system, s plus p2 s plus pn. So, and the p typically must be greater or equal to m. Okay, I'm sorry, I mean n, not p. So n is equal or greater than n. Okay, for causal systems. So, okay, so you can, let me see if it's, yeah. So you can now, in this closed loop system for higher order system, so this is nth order system, see, because you have n poles and m zeros you have for this system, and m zeros. So you can factor out z1 from here, z2 from here, zm from here. So what you're gonna have, you have zm, z1, z2, z3, zm, and what you're gonna have here, you're gonna have 1 over z1 s plus 1 over z2 s plus 1 until 1 over zm s plus 1 in the numerator. I'm going to do the same practice and factor out the p's. So you're going to have p1, p2, p3, and pn, 1 over p1 s plus 1, 1 over p2 s plus 1, and clear everybody? Yes? Yes, everybody? So, these are constant numbers. Yes? So, I can say this is as a gain, K, capital K. Then I'm gonna name this, or this, say. I'm gonna say T, this, I'm gonna name this T, M. So this is gonna be T1, T2, Tm. So you're gonna write as T1s plus 1, T2s plus 1, and Tms plus 1. And the denominator, I'm gonna call this T prime. Change the color. I'm gonna call this as T prime n. So this is gonna be T prime 1, T prime 2, T prime 1s, T prime 2s, and this is gonna be T prime ns plus 1. Okay guys, do you know what, we have a technical name and we name it as gain of transfer function. This is technical name, gain. DC gain of transfer function. This is when happens when you put S equal to 0. DC gain. Okay. So if you now put S0 here, what's the gain of this system? What's the gain of that? Put S0 in all places. The gain of the 0 is what? K here. The gain of the system. We have to know about this. Okay? This transfer function. So now this continues. You can write this technically as multiplication of, this is multiplied, I from 1 to M TIS plus 1 divided by multiplication of J plus 1, this is J. Let me rewrite it. Multiplication of J plus 1 to N, this is M, T prime of JS plus 1. Here we go. This is a standard notation of high order system in linear control with the DC gain of the K here. Clear, everybody? Yes? Can I go to the next page? So we ended up, in summary, x over y was k multiplication of I from 1 to M TIS plus 1 divided by pi j from 1 to N T prime of J S plus 1. Because in the previous class using MATLAB Simulink, you know that how to calculate multiple poles or roots of the system using the solve command in MATLAB, remember? So now, having this in the hand, I'm going to define a new things in control with the name of system type. System type. So system type being determined by this capital N, I'm putting here capital N, this is not this N, Sn. I told you when I taught you the Laplace transform that what is this in control theory? What is this? What is this in mathematics of high school? And what is this in mathematics of high school? Huh? What is Laplace of d over dt? Look at your notes. Is S. Guys, I'm disconnected. Hello? I have to shut it down. What is this? Read it for me. Yes. This is high school. This is not in university. Okay? What's in decoration Laplace? Go and look at your notes. I taught you at least 100 times. What's the Laplace of integration? What? What is Laplace of integration? Yes. So this means in high school language, this means what? Okay, Laplace of integration is 1 over s. So when you see 1 over s means what in high school? Guys? Okay, you didn't see integration in high school, guys? In high school, you never did derivative and integration? Truly? Are you kidding me or you're serious? Oh, that's why. No, because in my country they are teaching us everything in high school. I'm sorry, guys. So, okay. So, okay, when you see what I taught you in this class several times, remember, go to see the lectures. I have the proof, okay? So, when you see 1 over s means integration, okay? When you see s means derivative, that's right? See what I'm saying? So, system type. So, you have here 1 over Sn. It means what? 1 over s to the power of m. You have n. N what? N what? N what? 1 over s. What is 1 over s? I just told you 30 seconds ago. So 1 over s to the power of n means that you have n what? Okay, guys. 1 over s means integration. Yes. Means you have n integrator. Integrator. Okay. This 1 over s to the power of n means you have n integrator. That's right. Everybody agree now? Yes? Good. So, system type says your system is type 0. This is definition. If n is 0, means your system has no integrator by itself, not by adding controller. Understand now what I'm talking about? So, if that's the case, we're going to apply 3 inputs to the system. Our famous step, ramp, and parabolic to define new parameters in control. System type 0 when has no integrator by itself. So let's go for the step. A step. I taught you about the final value theory. Remember, ESS was the limit of S G 1 plus G. When you have a step, okay, so this is gonna be, I'm sorry, I'm stupid. X to the system, 1 plus G. So when you have a step, your X is 1 over S, you know it. S multiplied by 1 over S. 1 plus this function, K S plus 1 Oh, let me keep like that, guys. Yeah, let me keep like that. I don't want to go in. Hold on. Okay. And G. Okay. Because your system has no integrator. Okay. And it's 0. Okay. So when S goes to 0, when S goes to 0, this S with this S goes to New York. So this is the limit of 1 over 1 plus G at S0, because this is G of S, that's right. Okay. This has a technical name, guys. This has a technical name. When your system is type 0, the name of this is KP. Why KP? Because its technical name is static position error constant. This is technical name of this. Static position error constant. Okay, so you see that if your time, if you see that your system is type 1, means in the closed loop in the closed loop in the transfer function has no integrator. Okay, so its steady state error signal becomes 1 over Kp, knowing that Kp is G at 0. Here we go. Okay. So now for this system type 0, let me apply ramp means 1 over S square. So ESS of the ramp becomes limit of S in input 1 over S square 1 plus G when S goes to 0. This S with this S goes to the Denver, and what you get is this. Final value theorem. So when S goes to 0, this becomes infinity. Meaning that if your system is type 0, means has no integrator by itself, not by controller. Okay, so if you apply ramp, error signal goes to infinity. C, let us apply parabolic 1 over S cube. So it say ESS is the limit of S multiplied by 1 over S cube 1 plus 1 over G. Simply you see that this is going to be infinity. So done with this case. Let me define new parameter that we're going to use in control. When your system type is 1, means n is 1, means x over y gonna be k multiplication of ti s plus 1, and you have a s here because this is the power of 1, pi t prime j s plus 1. This is system type 1. Okay. If that's the case, now let us begin again. Oh, I say apply a step means 1 over s. So ESS gonna be a limit of s in 1 over s 1 plus 1 plus g when s goes to 0. So this is gonna be a limit of 1 divided by 1 plus, let me I name, when you guys, let me, don't do that. Good here. Okay, look at here, guys. When I put S0, this is gonna be 1, this is gonna be 1, remaining gonna be 1, the remaining gonna be K over S. S goes to 0, right? So, everybody agree? Yes? Okay. This is gonna be 1 divided by 0, infinity. 1 over infinity, 0. So when system has one integrator inside itself, the steady state signal gonna be 0. One integrator inside itself for a step. Now, let me apply. You are done? Let me apply ramp. ESS gonna be limit of S and ramp 1 plus again K over S, because the rest is 1. That's right. When I put 0. Okay. So this with one of these goes to hell, and you can write this as this 1 over S. You know what? Let me don't do that because I want to define a new parameter. Yeah. Okay. I'm gonna put G of S plus S G of S when S goes to 0. This equals to a limit of, if I put S here, this, and I'm gonna keep it here, G0. Bear with me. Here I'm gonna define a new parameter. Name of this that you're gonna see in the lead lag compensator, KV, means static velocity error constant. So for the ramp and system type 1, ESS is 1 over KV. Now I have a question from you guys. If you want to make a steady state error signal, what you gonna do with the KV? You want to make it 0. What you have to do with the KV? Make it smaller or bigger? Bigger. What you said means control engineering. You have to make KV bigger. Got it? Yes? So let's go to parabolic. Para 1 over S cube. ESS is the limit of S 1 over S cube 1 plus G. I don't want to waste your time. It's gonna be infinity, no doubt. So when I said your system is type 0, means your system has no integrator by itself. When I said system is type 1, means has integrator, one integrator by itself. Has means has 1 over s. Can I go ahead? So now let's go to the last type. Type 2 system means how many integrator has? How many? 2. Means it's gonna be k pi tis plus 1 s square t prime j s plus 1. The system has 2 integrator rates. So if that's the case, ESS, when you are applying the step input, gonna be a limit of s again 1 over s, and it's gonna be 1 plus k over s squared. When s goes to infinity, it's gonna be 0. No doubt. When you apply ramp, ESS gonna be a limit of s squared 1 k over s squared, s goes to 0. This is gonna be infinity. To make it clarify and make sure I'm doing right because I'm driving with you. This is gonna be a limit of 1 over s. This s goes here plus k over s. S goes to 0. So this, I'm sorry guys, this is gonna be 0, not infinity. That's double integrator. And now I'm defining the new parameter again. When you have parabolic, ESS is the limit of s cubed 1 plus g. I'm keeping like that. This with one of these goes, and you get 1 over s squared. 1 over s squared comes down. S squared plus s squared g when s goes to 0. This goes to 0, and this is gonna be 1 over s squared at g 0. The name of this in control of linear systems is KA, means static acceleration error constant. So for the parabolic, for the system type 2 is KA. So if you want to make this 0, do control engineering and select this or make this KA big. Understood? Being said, when you are done, let me know. Done? Being said, I can make a table here. ESS we are talking about. Oh. Type 0 system, type 1 system, and type 2 system. Means has 2 integrator, 1 integrator, and 0. Here is the step. Here is ramp input. Here is parabolic input. So as you have seen, this is gonna be 1 over Kp. Change the color. 1 over Kp. Infinity. The other one was 0, 1 over Kv, infinity. 0, 1 over Kv, infinity. And 0, 0, 1 over Ka. Being said that Kp is open loop transfer function at S0, Kv is S G of Gs, and Ka is S squared G0. Understand everyone? Yes? Good. And we can judge system based on these. For example, when G is 1 over S in S plus 2 zeta omega n, and here you have omega n squared. Do you remember this? Huh? This was for the massive spring damper. That's right? That we drive together. What's the type of this system, guys? Okay. Type 1. That's right. So if I apply parabolic input, it's a steady state error signal goes to 0. Yes? Everybody? Understand? Parabolic. This is type 1. If I apply type 1 on parabolic, it's the steady state error signal goes to how much? 0. Huh? But if I apply ramp, it's going to be 1 over Kv. Understand? See what I'm saying? So this is type 1. There we go. Just like this. Type 1. Okay. So I see, because I was looking for this. Because I'm saying that this is 0, guys. Right? Did I copy it here correctly? So is it step is 0, 1 over kV, and I see that this is infinity. Okay, so let me double check everything because I'm teaching from my mind. 1 over, what is that? Type 0. Type 0, so this is 1 over kV, right? Ramp is infinity, and this is infinity. Oh my god. Type 0, infinity, infinity. See, always double check. So type 1, first type 1, 0, 1 over kV, infinity. 0, 1 over kV, infinity. Great. Type 2, where's type 2? 0, 0, 1 over kV. 0, 0, 1 over kV. This is the table, not the previous one. Okay. Understand? So if we apply parabolic, it's gonna be infinity. So CESS gonna be limit of S parabolic 1 plus omega n square S in S plus 2 zeta omega. Mass spring damper. Mass spring damper has one integrator. It's type 1. This with this goes is 1 over S square. S square plus S omega n square in S plus 2 zeta omega. 1 over 0, infinity. If you apply ramp, gonna be 1 over kp. Apply step, gonna be 0. Understood, everybody? So you see that this is mass spring damper that I taught you step by step. Okay. Done? So I'm going to stop it here because the next class after the break I'm going to teach you the Rolf stability criteria. Rolf-Hurwitz stability criteria. And after that eventually I'm going to teach you PID and root locus, and finally, if we have time, dead lag compensator. Okay? Thank you guys. Just fix this table, please, because I mixed up the sequence from the previous pages. Okay. What's that? Oh yeah. Yeah. Yeah, that's the delay I have from the New Year. Okay guys, let me stop.